appreciate everybody for calling in. We've got a great hour ahead of us here. This is the monthly meeting of the East New England chapter of the Vertical Flight Society. So thank you so much for joining. Those of you who are members of this chapter, really appreciate you guys taking some time out of your schedule to participate in this. Today we've got just a great guest speaker that I'll be introducing in a minute here. But first, I just want to talk a little bit about the Vertical Flight Society. As many of you know, it is primarily a technical society, and so I would encourage you to consider joining the society. A number of events, actually, as it may happen, are coming up, and so as soon as tomorrow, the Sikorsky lecture will be given, and this year's winner is Dr. Mark Tischler from the U.S. Army, and so and he's going to talk about flight control systems for rotorcraft. So it should be a fascinating lecture, and that will be tomorrow at noontime is when it starts Eastern time. So tune in for that if you can. I think that's on a different, it's on a YouTube channel of the Vertical Flight Society. So I'll actually be introducing Dr. Tischler in that. So you know, I appreciate you tuning in for that, and be a very interesting lecture. Also, you know, Forum 76 starts next week. It's gone entirely virtual, but it's still a very similar format to years past, just not in person. So we have a number of panel discussions. So you have the industry CEOs. We'll be talking, I think, on Monday. As well as some R&D folks from the Army and the Navy and the various services, and then the following day begins the technical papers that are given throughout the day. So if you haven't registered for that event, I recommend it. It's just a great if you're interested in technical aspects of rotorcraft, there's no better place to be than Forum 76. You know, in addition, you know, Vertical Flight Society allows you to get together with like-minded professionals and network. It allows you to stay up on the latest industry technology. They put out a great monthly, or I guess it's quarterly magazine, Vertiflight, which really gets you up to speed on all the different aspects of rotorcraft. So if you haven't considered it in the past, please consider joining. It's a great society. Today, now I'll start with our program and guest speaker today. So today we're very lucky to have Joe Twomey. Joe is the chief test pilot for Bell, and in particular the 525 Relentless. And so Joe's going to talk to us today about the flight test program for the 525. And I'll just give you a little background about Joe. Joe graduated from the Naval Test Pilot School in 1993, reported to the Navy Rotary Wing Aircraft Test Squadron, testing performance, flying qualities, and systems on the H-53 and other Navy and Marine Corps helicopters. In 2002, he returned to the Test Pilot School as a senior Rotary Wing instructor pilot, and in 2004, he reported to the Air Test and Evaluation Squadron on HX-21. At Pax River as the MH-60S Government Flight Test Director, and shepherded in air ambulance program through its entire test program in less than 1 year, ensuring that it deployed in theater with no major deficiencies. In 2008, Joe joined the civilian test world, starting at Sikorsky as an experimental test pilot for the H-series, the S-76D and S-70I helicopters, then with Avian Engineering as an MQ-8B Fire Scout UAV test pilot and lead courseware developer and instructor for NAVAIR's Test and Evaluation University. Finally, in 2016, he joined Bell, supporting the 525 fly-by-wire helicopter and V-280 future vertical lift programs. He conducts structural evaluation, rotor characterization, height velocity diagram, category A profile development, degraded systems, extreme weather, and fly-by-wire control law development tests. In 2019, he was selected as the inaugural member of the Society of Experimental Test Pilot Cockpit Magazine Editorial Board and achieved certification as an ODA Unit Member for FAA certification testing. Joe has also been nominated to serve on the Vertical Flight Society Technical Committee. He has over 3,800 hours in over 50 rotary and fixed wing unmanned aircraft, and is an associate fellow of the Society of Experimental Test Pilots. So we can't wait to hear Joe's remarks, and so I'd like to ask Joe to say a few words. Joe?
Thanks, Harry. Can you guys hear me?
Yes.
Okay, great. So I'm dialed in on my phone here. I'll share my webcam and get the presentation going. I really appreciate the introduction. Well, it sounds kind of funny because I was mowing my lawn yesterday, just like everyone else. I'd also like to take a quick second to thank the VFS for having us on board today to be able to talk about the 525 Relentless program and an update on where we are in the test program, how the aircraft certification testing is going, and what we can expect, hopefully, out of the aircraft here in the very near future, and some of the features that the 525 will present, helicopter operators worldwide, and what differentiates it from more conventional helicopters. So I will bring my screen up, hopefully successfully, and we'll begin the presentation if you guys are all ready. And once again, and thanks for everyone for dialing in. Everyone's schedules are busy and things are complicated right now. And for you guys to take the time out of your day to allow me to talk about the helicopter, really appreciate it. And we'll begin with that. So like Harry said, here to talk about the 525 Relentless program. This is a brief that was put together by the program itself. So some of it kind of sounds like marketing. I'll try to throw in what I think are the important facets from test pilot's perspective. And if you guys have any questions, I think Harry's going to be collating, or Lauren is going to be collating the questions. I'll try to do my best to answer your questions to the extent that I can. And if I don't know, then I'll just tell you. Okay, my webcam has been closed. Well, with that, I'm going to go ahead and go to the next slide, which is just the program update. So real quickly, we currently have 4 aircraft in the flight test program. Ships 2 and 3 are fully instrumented, and they have been assigned primarily to flying qualities and performance testing, as you might imagine. Ship 14 is a little bit more production representative. It's only partially instrumented, and it's been trading its time between flying qualities and performance and then more systems type of testing, and some of the testing that requires the aircraft to be a little bit closer to production standard. Then we've got Ship 15 that's also in the livery as well. It is not instrumented at all. It is our most production representative aircraft to date. And it's if you take a look at its schedule in the future, it's got a scope and breadth of systems testing, function and reliability testing that's coming up, and anything that requires us to be very well conformed to a production standard. Amongst those 4 aircraft, we've got about 1,600 flight hours over the course of the program to date. I came on board shortly after the aircraft started flying, which was in 2016, and like I said, those aircraft have pretty much borne the brunt of the testing to date, including the testing that's been taking place here in Texas, North Texas. We've also gone basically all over Canada, up to Thompson and Yellowknife in 2017 and 2018 to conduct our cold weather testing. We need to get as close to minus 40 degrees C or Fahrenheit. They cross over at the same point when it gets that cold. It's been interesting doing some stuff up there. And if anyone has any time, you can go to, there's a YouTube channel. I forget, I think it's run by the same guy that does Space Pilots. They've got some footage of us doing some of our lower speed and other island qualities types testing up there in Yellowknife. Simultaneously, we sent aircraft 14 to Rome, New York to do snow testing, and that's just on the eastern side of the Great Lakes. So we tried to take advantage of lake effect snow and the extreme weather they get there to get our snow certification data, in a report format that we've presented to the FAA, and we're waiting for acceptance of that, or then for them to tell us that we need to go back and redo some of that testing. Last year, 2 years ago, we simultaneously had aircraft in Yuma, Arizona, and Alamosa, Colorado, to do high altitude and hot weather testing. I got a chance to take part in both of those test programs. A team of about 30, 35 people at each of those sites to help pull that off. interesting time to go to those 2 locations to check out how the aircraft performs at the upper or outer edges of the performance envelope that we expect. Since then, in 2019 and a little bit in 2020, we started to bring customers in to do some of our initial customer evaluations to take a look at the aircraft, give us some feedback on what they think, and not only from a flying perspective, but also from the cabin perspective. I mean, this aircraft is designed to fill an area in the marketplace that primarily serves the offshore oil and gas customer. At least that's its initial market foray. So we had some people in from Norway who deal with working on the rigs out in the North Sea. They had a chance to climb all over the aircraft over several days. And then some of their pilots actually went through our ground systems course and then took the aircraft out on a qualitative evaluation flights. And we'll take a look at some of those little tidbits of feedback that they gave us. But they like the aircraft. It offers some things that are unique to a new program that you won't necessarily see in more legacy types of aircraft. And like I said, we'll take a look at what they said. For the next slide, this is part of the parts of the test program that have either been completed or are ongoing. And as you might expect, we've pretty much done all of the flying qualities performance throughout the intended gross weight and CG envelope and altitude spectrums that we envision for the aircraft. And in fact, if you take a look at our gross weight and CG, due to FAA certification requirements and just from engineering analysis and that kind of thing, we've gone outside the structural design envelope that we intend for the operator to use, so that we can make sure that when people are operating the aircraft within the operational envelope, that it's a safe place to be with the aircraft, and it's performed really, really well. It's I can't say enough about how well the aircraft is performing for us. In addition, of course, we've done performance and propulsion certification, and I know a lot of you guys are associated with GE in some way, shape, or form, and you might ask, how does performance and propulsion differ from an aircraft manufacturer versus an engine manufacturer's standpoints? For us, propulsion not only includes the engine, and we're very happy to have the CT7 on board. I've flown a lot of T700 or CT7 variants, and it's a really good solid engine. So thank you guys for that. I really appreciate having the horsepower available when we need it. For us, to get back that little check mark, the propulsion also includes our dynamic components, the main gearbox, intermediate gearbox, tail rotor gearbox for basic drives, as well as our reduction gearboxes. We have 2 of those, and then our accessory gearboxes, we have 2 of those as well. Because it was a clean sheet design, I went to design engineers and said, hey, listen, we want you guys to, if you could develop a propulsion system that you thought was going to be, the best ever, you're willing to put your name on it, please draw it up and tell us what you think. They came up with a clean sheet design that differs, from our legacy 214, 212, 412, UH1, the Yankee and Zulu, very tall types of gearboxes to, much flatter with systems separated for reliability criteria that we need to meet. They're very, very proud of it. We're very happy with what they've been able to achieve. This aircraft will have the run dry capabilities that the FAA requires. In fact, from what I understand from the ground testing, we've exceeded that. With Ship 2, it's been taken out of the test program now, and it's being modified to go into a ground testing as a ground test vehicle. So we'll run out the airframe to the end of its life, testing those dynamic components here coming up. I think that's going to be happening in November, and that'll validate the ground testing on the bench that we've done with the other systems. We've also taken a look at the scope and breadth of engine APU operation, and then used engine performance, obviously, for Cat A takeoff and landing profiles. And I kind of have Cat A put in there in between handling qualities and propulsion, because there's a little bit of a crossover there when you talk about being able to take the aircraft off from, say, a runway or an offshore oil and gas platform, and then ensure that in the event of a single engine failure, that you're able to return the aircraft back safely to the takeoff point, or continue to take off if that's what the pilot has determined is the safest course of action. So we've gone through that. In fact, Aircraft 3 just got back from up in Amarillo doing crosswind Cat A testing over the past 2 weekends, and just to validate our low wind, no wind profile is still valid when you've got winds from varying directions. So that went really well, and they're glad to have those guys back. Dynamics, that gets into flying qualities and your basic stability, and includes statics to a certain degree, and we've done that. And then other aircraft handling qualities development in terms of how the control laws provide feedback to the pilot and the crew. We've got a unique feature, we'll talk about that I think in a little bit, called auto rotation entry assist. So we've taken advantage of the fact that we've got a fly-by-wire system that we'll talk about extensively in later slides, to allow the aircraft, in the event of a dual engine failure, to automatically decel the aircraft to lowest rate of descent, and then control the collective automatically to retain NR at the desired rate. The pilot can obviously intervene at any point to override those or trim to a different condition, but at least for that initial reaction, when you might be paying attention to some other aspect of a particular mission, and maybe you're punching a button, or you're taking a look at a radar or FLIR or something, whatever the installed system might be, that you might not be fully attentive to the task at hand. Boom, something happens and the aircraft takes carry, then it allows the pilot to get in the loop and continue to fly the aircraft down to a safe landing. We talked about some of the destination testing that we've done. I don't need to go back over that, but in addition to some of the destination testing, some of the other testing that we've done here, to the extent that we can, given that it's Dallas and it's pretty flat, we've done slope landings to take a look at how our weight on gear versus control laws, how they interface. That's no problem with that at all. We've been able to develop an envelope for that. It's 10 degrees all the way around, except for the nose, and that's a tail clearance issue and not a handling qualities issue. We also sent out earlier this year an aircraft to California to do noise certification. They've got the right weather conditions for us to be able to do that. We would have preferred to do it here, especially with COVID, but we had to go out there because they've got the low humidity and the temperatures that we need, plus the instrumented range that's required for that development. That went successfully. We were able to mitigate any of the COVID restrictions that were in place, especially given where California was at the time. So those guys were very helpful. FAA was very helpful. I'm able to knock that out. We've done some other cats and dogs types of things that are required. Fuel systems calibration, obviously you need to know how much gas you have. And then fire extinguishing, we need to be able to put that out if the fire happens to start to exist somewhere outside of the combustion chamber. Then we had a very successful period for cabin egress. We did one, as a matter of fact, that I was part of. Probably the biggest challenge with that one is getting people together that haven't taken part in the other scenarios that the FAA requires us to demonstrate. And so it takes a lot of people. You'll see in a future slide that we've got room for 16 people to be in the cabin, in addition to 2 pilots in the cockpit. So that's 18 bodies times, between 4 and 6 different scenarios. All of a sudden you're talking, upwards of 100 people that you've got to get in, because you've got to have backups as well in case somebody doesn't make it, gets stuck in traffic, gets sick, that kind of thing. So that was a challenge in terms of the logistics involved. It was not a challenge to get people to successfully egress out of the aircraft. It was interesting. It doesn't sound like it'd be that interesting, but it was fun to watch the videos afterwards. In fact, the last test that I was involved in, we were able to egress 18 people out of the aircraft in 19 seconds with no briefing, nothing other than like a standard FAA type of briefing that you would give somebody, walking aboard an aircraft, whether you're on Southwest or American or Delta, you can run the gamut. Okay, some other testing that we've got ongoing. We've still got some flight characteristics stuff that we got to do. Part of the stuff that we do requires us to do company testing at a time. To the extent that we can, we try to take credit for that if the FAA accepts the data, but they want to take part in some of the testing, especially given that this aircraft is the first commercial fly-by-wire helicopter to be put forward for certification. So the FAA is very interested to take part and see just exactly how the aircraft works and functions and that kind of thing. So we're happy to have them on board and share what we've learned about the aircraft and get them some experience in it and then move forward towards a certification. We're doing avionics company tests right now as well. Basic navigation systems, some of the health and usage monitoring systems, rotor track and balance, communications, the whole 9 yards, radar, that kind of thing. And then we've got interior compliance to make sure that the aircraft is conformed properly and that everything is, from a crew standpoint, is where it needs to be. Some of the stuff that we have upcoming that has yet to be completed, once again, we got to continue on with the avionics and the autopilot or flight director, however you want to look at it. We've got to do some demonstration points for handling qualities and performance for the FAA. It's not going to be the complete scope and breadth of what we've done for company testing, and you wouldn't expect that. But we've got to show them, the most extreme cases that we identified during our company tests, so that we can prove to them that we've met the intent of the federal aviation regulations. We've been doing some work on engine APU operations. I think it was week before last. I was out last week, but the week before that we were doing engine in-flight restarts, APU engine restarts, that kind of thing, operability and control in terms of static droop, and how does the engine respond to collective inputs and flight control inputs to make sure that that synergy between the airframe and the engine itself functions to the expectations that an operator and the certification authorities would expect. Electrical systems and lighting, as you might expect, just got to make sure you can fly at night for the lighting, and then electrical systems, when you turn the switches on, that all the systems get powered, and then when systems start to drop offline, should they drop offline, that the different profiles in terms of how the buses react to power failures and that kind of thing actually provide power seamlessly. That we shed things when they're supposed to be shed, and then we retain the items that are required for safety. We got a pretty big program coming up for function and reliability. I think that's about a 150-hour flight hour program, and we can take some credit for that. Negotiations with the FAA will determine how many hours we actually need to fly on that, but they're going to be in the cockpit next to us, just flying all over the place, pressing all the buttons, doing all the things that you need to do to prove that the aircraft isn't just like a one-trick pony or a one-hit wonder, that you use it over and over day to day, that it continues to work. Some ground tests that we've done bird strike. The engine, the CT7, has been certified. You guys knew that to those press releases. I think that came out last year on that. EASA has validated that. We've done a bunch of crew air management. There's some regulations that don't necessarily apply to this aircraft because of the date that we put it forward for application certification or certification application, but we're still trying to maintain compliance with that. And so the FAA has been a team member of ours for several years now, making sure that from a crew air management standpoint that we've considered all the different things that can be gotchas if an operator were to go out and do something. And we're trying to anticipate those types of things so that we can provide fixes before they actually become issues in the fleet. Most of our fatigues and supplier tests are complete. Drive systems, they're also nearly complete. Most of that that exists still is in the ground test that's coming up on Ship 2. And with that, our certification test program is we're making forward progress, and we're nearing completion. So hopefully, sometime in the upcoming year, that we'll get our testing complete. The data will be provided to the FAA, and we can get some of our sign-offs. Okay. This one was labeled performance in the program. I changed the features just because I thought it was a little bit more appropriate to the content that is going to follow from here. This is going to sound a little bit like marketing, but it's kind of unique in some respects to what somebody will see out there in the fleet. Probably the biggest one that we've got going on is the triple redundant fly-by-wire flight controls. That's, like I said, unique. There are other aircraft out there, rotorcraft, that have fly-by-wire flight control systems, but none that have been put forward for civilian certification. When tilt rotors came around, so Bell's been doing fly-by-wire for 30 plus years. When you start talking about anything that's got a tilt rotor type of thing, V22, XV15 was mechanical, but AW609, which was a joint Augusta-Westland, now Leonardo Bell program, until we sold our shares, that was all fly-by-wire. So we've been doing this for a while, but it's the first time that it's been applied to a civilian helicopter. A couple of the military helicopters that have have fly-by-wire. CH-148, the Sikorsky's built for the Canadians. That one's probably the most well-known. And then Sikorsky also had a foray for the Army to take a look at conceptually what a Black Hawk might look like should it have fly-by-wire flight controls. And we'll talk a little bit about how Bell's philosophy differs maybe slightly from other manufacturers. In addition, the newest one that's out there is CH-53K, fully fly-by-wire, another Sikorsky product. So you can see it's starting to be, it's been fairly well accepted on the military side, but on the civilian side, it's a little bit, it's kind of funny. The fixed-wing guys seem to get the advantages of it, and the regulations have followed suit. But that's probably, I'm sort of alluding to future discussion items. But probably one of our biggest challenges that we've faced so far isn't necessarily with the airframe or the power plants or the fly-by-wire system. It's the fact that the regulations that the FAA is bound to find compliance with have not followed the pace of technology. And I think, if you talk to somebody from Boeing or Airbus or anywhere else, they probably say the same thing in terms of, how do they take, this piece of hardware and get it up into an operator's hands so that he or she can use it, generate revenue, to move people around, to move cargo around, whatever. So, like I said, most of the stuff that we've done, we've been pretty happy with, and it's followed our expectations. But we're still working on, how we get around some of these regulations that were developed, literally, 50s, 60s, 70s, and try to get them up into the 21st century. So fly-by-wire, 5-bladed main rotor. Bell has built, multi-bladed rotor systems for quite a while, but for Bell, with the exception of the 139, which Augusta-Westland has, and that was a joint venture between Augusta-Westland and Bell as well. This is the first basically sleeve and spindle fully articulated head that 5-bladed head that Bell has built. We start to get in larger helicopters, you have to kind of go away from something soft and plain that bears its load through elastomers and different composites and stuff like that, and get into something that what we see today. And it's worked out pretty well. So it's a good system. We've got a canted tail rotor. We'll talk about some of the issues that presents. So there are other aircraft out there that have canted tail rotors, H-60, H-53. We've run into some of the same challenges with a canted tail rotor that our fellow OEMs have run into, but we were able to deal with some of those, as opposed to dealing with that mechanically, dealing with it through software. We've got GE engines on there, 2 of them, provide plenty of horsepower for us for the design envelope. With the fuel that we got on board, we got really good range, so the operator is going to be able to go pretty far offshore with their employees to drop them off and to the platforms and bring them back. And then whatever the follow-on kits are for search and rescue and some of the other things that we envision for the aircraft, will provide a lot of flexibility. And when the range really comes in handy when you're flying across someplace like Canada, where you don't see a fuel stop very often. You've got to get a long ways, and then we were able to exploit that to a very large degree, going up to Thompson especially. We've got a small APU on board. It's not huge, but we don't need a lot. We need a little bit of air and a little bit of power to be able to start the engine and run the systems, and we'll talk about what some of those systems are. A couple of things, though, and we'll talk about this in another slide where we talk about design philosophy, is some of the unique features for the aircraft. We really concentrated to a great degree on the guys in back. Really, that's what the aircraft is about. It's about carrying people and things, places. And so what you'll see on our doors, we got a sliding door. It's about 5.5 feet wide, which is huge. And you take a look at the windows, and the windows are enormous. So it gives a lot of visibility to the people in the back. We've got a lot of glass in front to give us visibility from a basic flying standpoint. But when you take people places, they want to take their stuff, especially if they're going to spend time out on a platform for 2 weeks to 30 days at a time. So we've got a really large baggage bay, and that's feedback that we've gotten that that's something that customers are really looking forward to. And when you take a look back there, you're like, oh man, that's really big. You can put a lot of stuff in there, carry a lot of things, and I'm sure the operators are going to take advantage of that. In the back, if you take a look at the lower left, best-in-class seating comfort, the seats are huge. They're about 20 inches wide. They're not, they don't crane your neck forward like you see in some other military aircraft where they're not necessarily concerned with passenger comfort. Obviously, that's a primary concern of ours. We want people to want to get into our aircraft, and we want them to walk out and not feel like they've been put through a torture session. We want them to come out fresh and invigorated and happy that they were on our aircraft. So up in front, from an operator standpoint, going to the pilots, we want people to be able to look outside. We stopped on our way up to Canada and took a look at some of the jet aircraft that are there, and you take a look at those guys, and they've got very tiny windows. Now, they've got different concerns that we have, but from a helicopter standpoint, you want to have that visibility, because our operational envelope goes everything from 35 knots backwards to 175 knots true forward, and you need to be able to see stuff. And not only do you have synthetic vision and the moving map displays and things that the Garmin G5000H provides, but there's really no substitute when you're clear of clouds to being able to look outside and see what is really out there. So really good cockpit visibility. I appreciate that as a pilot, and I'm sure the other pilots out there will as well. We know that this aircraft is going to be operating over saltwater to get to the offshore oil and gas fields and platforms. So from the get-go, we've provided corrosion prevention in the aircraft. If you take a look, in the guts, because especially on ships 2 and 3, they don't have the interior paneling set up, not like ship 14 and 15. So you get to see, for the metal structural members that we have, they're all zinc primered, and obviously the primary airframe is built out of carbon fiber, so that's got its own corrosion prevention just built into the fact that it's basically flat fabric and glue. A lot of thought went into how we were going to, what the intended operational envelope was going to be for the aircraft, how we build the best aircraft to deal with, not only the people inside the aircraft, but if you're an operator, what are the things you're worried about? You want to make sure that the aircraft is ready to fly when you need it to fly, that it's not going to break when it gets to its destination, that the people are going to want to get into it, and that it's going to be cheap to operate. So we'll talk about some of that stuff later on. That's we take a look at some of the challenges that other people have had with the airframes. We try to anticipate those so that when they buy this brand new aircraft, they've got a good rationale behind it, like why they chose us over someone else. And just real quickly on the lower right-hand side, we've taken the aircraft to minus 40 degrees C all the way up to 51.7 C, 125 Fahrenheit. So it's been, all over the place. Everywhere from 0 density altitude up to, I think we've flown it at 14,000 density altitude. So and everywhere in between. So, okay, got to move my picture around. Okay, so this could be a question or a statement. This one's really a statement. So when we talk to people about the 525 and what makes it not necessarily different, not necessarily better, well, different, but not necessarily better, but just some of the things that the lessons learned over the past that we hope translates into something better. This is the list that we came up with. You got to get people places, and they got to be able to, get off safely, not injured, not hurt. Got to get there. So we took a look at that and said, okay, from the crew and passenger standpoint, these are the things that the aircraft needs to have. It needs to be reliable. It needs to be functional. It needs to be something they can get into, like I said before. And if something does happen, that we've got enough redundancy and backup systems that either the aircraft can continue to its destination, or it can divert to someplace that's safe to do so, and then deal with the issue from there. And if those opportunities don't present themselves, that you can safely land the aircraft, shut the aircraft down and get the people out safely. So those are some of the, probably the basic tenet that we use to design the aircraft. But we didn't just forget about the other folks that are part of this puzzle that keeps the aircraft, reliable. We have to make sure it's maintainable as well. And if you take a look at this aircraft, it's a tall aircraft. So when you've got height and people working on stuff, you got to make sure that it's not slippery. So we've got non-skid on the top of the aircraft. You got to give them, a work platform to work from. So if you take a look at the hydraulic access panels, they fold down and they're work platforms. So if you don't have stands available, these guys can get up there, they can open the cowling, and they can stand on there and work on the aircraft and not worry about slipping and falling off. We also tried to put everything accessible from the outside so that you don't have to dig way inside to fix things should they need to be fixed, or to replace things should they need to be replaced. So it's a pretty easy aircraft to pre-flight. It's a pretty easy aircraft to work on. So the guys, when they were putting pen to paper, they did a really good job. Let's see, like I said a little bit earlier, when they presented the opportunity to the propulsion guys to come up with a clean sheet design, they took full advantage of that and went and applied the latest technologies possible to ensure that we've got redundancy built into our systems, that we're going to have run dry capability, that we do have run dry capability throughout primary drive systems, to make sure that if something, if you have a lost loop or whatever, that the aircraft can continue for whatever the criteria are, and then safely land. Okay. We put in fly-by-wire, like we talked about, primarily as a way to increase reliability and maintainability, but also to reduce pilot workload. We've taken a look at, to a very great extent, on human factors and how that machine man or machine-person interface works, to make sure that we've taken the pilot's job from being, hey, I'm just there to fly the aircraft, to I'm there to accomplish a mission. And that might be lost to a certain degree, because some people think, okay, the mission is flying the aircraft. No, it's not. The mission is getting people from one place, or stuff from one place, or a combination thereof, to another place. And how do you do that safely throughout different environmental conditions, offshore, that kind of stuff. So we're trying to take that forget the term that should be used, but basically that mental workload aspect from the actual physical control of the aircraft, and trying to expand that spare capacity that a pilot has to be able to focus on, okay, how do I navigate, how do I communicate, and take it off of the aviate part of it, which is, if you take a look at historic designs, there was a primary emphasis on the aviation aspect, and now we've moved beyond that into the navigate and communicate. If any of you guys are pilots, aviate, navigate, and communicate have typically been the priorities for a pilot. We're trying to say, we'll take care of the aviation part, you take care of the navigation and communication, and focus on the mission. And that's going to pay dividends in later iterations and later kits, when the mission scope increases from transporting things and people into search and rescue and all kinds of other stuff that take a great degree of mental workload to accomplish. The aircraft is really comfortable. I've flown other aircraft where you get out of the seat after a couple hours and you're stiff and sore, and that can't just be ascribed to old age. They did a good job designing the seats, putting an environmental control system that keeps you cool or warm, depending on what the conditions are. The aircraft's got an automatic vibration control system that we haven't really had to turn on yet. We will when we test it, but with a 5-bladed rotor system, it's very smooth. And we also made it easy to get into and out of, whether that's via normal means or through emergency egress. We've taken a look at all the different structural requirements and made sure the aircraft meets those. I talked about IBMs. The aircraft is fully instrumented. It downloads all the data that it needs to, so that when you come back, like on a 747 or 777 or 787, the maintenance guys aren't relying on pilot feedback to tell them what's wrong with the aircraft. They can just go in and download it, and the aircraft will tell the maintenance guys what needs to be done to fix it. We talked about maintainer safety, and we talked about the other two bullets there for R&M and multi-mission. Okay, so this is a quick kind of an overhead shot of how the cabin is set up. You can see that the forward row and the aft row both face forward, as well as the third row, but then in the middle there's club seating. This is all done for comfort. One of the things that I think is notable is here, if you take a look at the right-hand side of the aircraft, each row has got a huge window, and those windows those pop out for egress if the doors are not able to be opened. But each row has got access to a door handle to be able to open that. So if for some reason there weren't any people in this third row seats, the people in the fourth row could go and open and slide those doors aft or push the windows out. When we did the egress test that I was involved with, the the guys on the outside, unbeknownst to us, they kept those doors shut, so we'd be forced to push those windows out, and we still did that using these push-out windows in the 19 seconds that I described. There's also J-tracks up here for the pilots, so that you can release a handle on the outside edge of the seat, and the seats for the pilots will rotate aft, slide aft and then rotate, so it's a little bit easier egress. I'm used to just climbing in and out of the seats, and most of the guys that have been on the program for a while just will climb out. But in the event, I think operators will probably end up using the J-tracks instead. Super wide cabin, 84 inches. And each of these seats are 20 inches wide. So plenty of space for people to sit and stretch out. Okay, then up front, we've incorporated Garmin G5000H. What's notable about this is there's two pilot or primary flight displays and two multifunction displays that each have a reversionary mode. So if you lose a PFD, the MFD becomes the PFD or vice versa. So a lot of work has gone into that to make sure that we've got redundancy and backups should a screen fail. Everything is controlled through the Garmin touch controllers, which is where you see the pilot's finger pointing. So everything is accessible through there. And what's notable about this picture to me, and it's probably not apparent to everyone, is usually in a cockpit, especially in legacy aircraft, you'll see switches and everything in the overhead. There are no switches in the overhead in the 525. The only control that's in the overhead is a rotor brake. So everything is clean inside. It's uncluttered. It's controlled. This lower panel here is for the flight director. That's a Garmin feature as well. And then all the engine controls up here. So there's these two switches here called the crank on, start, idle, fly, crank off, start, idle, fly switches. This is how we start your engines that you provided us. You just rotate a switch to the start and idle position, and it takes care of everything. It's got two acceleration schedules that we can control, but it's really the most straightforward engine start that I've ever experienced in 35 years of flying. Super simple. I know I'm running a little bit behind schedule here, so I'll try to speed it up. Talking about the fly-by-wire. Okay, so why fly-by-wire? It seems like we've made the choice, whereas other manufacturers haven't. Where we see the primary benefit is the improvement in safety that we believe that fly-by-wire provides. We can do a lot with it that you just can't do, or is very difficult to do with conventionally controlled bell cranks, push tubes, cables, types of systems. We've got 3 flight control computers, each of which has its own 2 independent processors. Any one of the systems is fully capable of flying the aircraft should we have failures. We've got, in addition to our primary power generation, in terms of electrical power, each flight control computer has got a permanent magnetic generator. So if we lose all 3 generators, there's still a PMG that provides power to the flight control computers. So if the rotor's turning, those things are powered. We'll see another picture here where we've taken advantage of the room that the aircraft provides and moved the systems around so that no critical systems are in the same zone. So if we take a bird strike or something happens, unforeseen, within an area of an aircraft that doesn't take out to any other systems. And as a part of being a fly-by-wire system, we've gotten rid of, this vast array of complex mechanical linkages, and then the associated maintenance that goes with those, and just replace them with wires. So there's one area where we do have mechanical linkages, and we'll talk about why in a second. But those are the primary reasons that we went fly-by-wire. So if you take a look at this next slide on system redundancy, you can see, especially on the right-hand picture, you'll see that the green, red, and the blue systems are the hydraulic power packs. Each of them are in different areas, so that you can lose 2 of them, and we still have another one that exists that's capable of providing all the hydraulic power that you need. Each of these actuators, which is this thing in the middle on the upper hand side, you'll see it's a blue body with red, green, and you can't see the blue. It's sort of there in the front. Each of the actuators has got 3 pistons that comes out of the top. Any one of those pistons can control the rotor head. So we can lose 2 lanes and still have a third that's a backup. So it's a pretty amazing system. Really, really happy to have it. And we've gone through failure mode testing and all that kind of stuff to to make sure that this isn't just talk, that it actually functions in real life. One of the systems that we use is we call the RASL, but it's the Relentless Advanced Simulation Integration Lab. It's actually hooked up to aircraft hydraulic power packs, aircraft flight control actuators, aircraft flight control computers. So anything that we do in the cockpit portion of the simulator gets translated into real live flight control actuator input. We can measure actual loads and determine if we've got issues and what we might need to do to fix those. And that's one of the benefits of simulation technology where it is today, where it might not have been available 30 years ago. Okay, we talked a little bit about mechanical links. If you take a look on the lower left-hand side, you can see that we've got a dual set of cockpit controls, a typical helicopter. The cockpit controls are mechanically linked, and that's just from a simplicity standpoint. Left seat, right seat, pilots kind of like to know what the other person is doing, and this is a simple way to do this without getting into bandwidth issues from a computing standpoint. Trying to determine, was that actually a vibration that caused the collective to move, or was it a pilot input that caused it to move? This simplifies, that level of calculation. Same thing with the cyclic and the pedals. So it's a very simple run. If you look up the floorboards and take a look in there, it's to me, it's from a design philosophy standpoint, it was a smart way to go. Everybody knows what everybody else is doing, and the trade-offs with that, I think, are far outweighed by the benefits. But essentially, on the right-hand side, by going with fly-by-wire, we've reduced single point failures by 70%. We have less parts. We have we're less subject to flight controls jamming, through wear or bad rigging or something, somebody leaving, FOD in the aircraft. It's obviously simplifies or improved safety, and it simplifies the rigging process because you don't have to sit there and go through and take up slack in a worn bearing or a belt crank or any of these kinds of things that you might see with, something like a 53, like a 53 Echo, a 53 Delta that I used to fly. There's also a big weight savings because you don't have metal all over the aircraft now that you've got to account for. So there's that. There's a couple more. So no mechanical links except for up here. We already talked about that. And okay, so one of the other benefits is reducing pilot workload. So we've got ergonomic side sticks. That's one of the things that you'll notice in this aircraft is in a conventional helicopter, you'll have a centrally mounted cyclic. There's safety issues with that, especially in vertical landings at high rates of descent. If your shoulder harness doesn't lock, unfortunately, in helicopters past, pilots have found their faces stuck in the cyclic, and obviously that leads to health implications. You don't see that with this aircraft. So for some reason, you don't get your shoulder harness locked or the inertial reel doesn't lock. You can pivot forward from your hips essentially and not hit something. So it's much safer. And once you get used to flying with the side sticks, it actually becomes very, very natural. It's a little bit easier to rest especially on the cyclic with your right hand, to rest your hands on the forearm rests and control the aircraft. Because we've gone with the side sticks, our control throw is about half of what you'd expect to see on a conventionally controlled aircraft. So you can find motor skills come into play there, and it actually works out really well. I prefer it over regular aircraft. Okay, let's see, single axis inputs. So when you've got, anytime you've got a high tail rotor, like we have on the 525 or other helicopters, or you've got a cannon tail rotor or some sort of, basically, two of those taking place, you get control coupling. So with a high tail rotor, if you pull up on the collective, you're going to get some lift, which causes a pitch implication, and then you can go through all these different iterations. We're able to take care of that control coupling that the pilot would normally have to take care of through software, and it makes it a very easy helicopter to fly. It's you get a person in there and they don't have any time in the aircraft, and they're able to fly it right away, to a very high degree of fidelity. That kind of thing takes a lot of, in a mechanically controlled aircraft, it's a very engineering intensive exercise to try to get rid of that. And the problem with it is when you go with the mechanical route is that you can only design that decoupling for a given set of environmental circumstances. So there's some compromise where you said, hey, listen, this aircraft is primarily going to operate at 4,000 feet density altitude at 150 knots at a gross weight of, say, 50,000 pounds. Anything outside of those constraints, results in control coupling that the pilot then has to take care of. We don't have to do that with this aircraft. The software knows how high it is, it knows how hot it is, it knows how much it weighs, the whole 9 yards. And we can take care of that, like I said, through software. Makes it pretty easy to fly. We've got some, like I said before, we've got vast, because like any helicopter, I mean, we go everywhere from 35 knots backwards up to 175 knots forwards. So we've got to take care of flight regimes that run that full scope and breadth. This aircraft incorporates automatic hover hold that's a GPS reference. So when you pull up into a hover and you release the aircraft, it not only maintains zero speed, but it maintains that position over the ground. Now you can translate by beeping up to 35 knots in any direction. Once you get outside that, it automatically transitions into an airspeed hold mode as opposed to a ground speed hold mode. It's got different, we can go through, it took me 3 days to try to explain it, but it's got heading hold, turn coordination, automatic bank angle hold. We've already talked about auto rotation entry assist. From an engine standpoint, it's really nice. You can pull the collective up into an engine limit, and it's got power hold. So it'll maintain that power level all the way through your climb, which is really nice. So you don't have to keep adjusting, from takeoff all the way up to your intended cruise altitude. That once again reduces pilot workload. We've got precise trim beeping. One thing that's real nice about that is, especially in airspeed mode, and even in ground speed hold mode, the control laws give the pilot visual feedback that says, okay, you've trimmed to X airspeed or X ground speed, so you know what the aircraft is trying to command, and then you can evaluate how well it's doing that. And at any point, the pilot can override. We also have collective tactile queuing. So if you are reaching an engine limit, you can set either max continuous power or takeoff power. When you reach that threshold, the collective will push down in the pilot's hand to let him or her know that, hey, you're about to exceed a limit that you've told me that you want to maintain. But if the pilot wants to exceed that, you can pull through and continue to go. So that's a pretty nice feature that you won't see in other aircraft. Sorry, I went 2 slides ahead. Okay. Once again, we've got full-time continuous stabilization for guests and other services. We talked about the control axis decoupling, primarily as a result of high tail rotor and canted tail rotor, and then any other coupling that might exist, whether it's the collective cyclic or pedal induced. Full-time 4-axis autopilot in all axes. And we've also got advanced modes that lay on top of that for flight director. So we've got altitude hold. We've got the ability to couple to approaches for navigation, whether it's DOR, GPS, whatever the basis might be. Heading hold, the whole 9 yards, depending on how it is that you're being vectored around airspace or you've been told to navigate to a destination. The aircraft will return to trim. So if the pilot decides to push the cyclic out of the detent position to override something, it will return back to that reference. Especially in fore and aft cyclic, it will do it in roll to a certain degree. Once you get outside a certain displacement laterally, the aircraft will say, okay, you want to maintain a certain angle of bank. It'll automatically do that, and it'll maintain it throughout until the aircraft runs out of fuel. We already talked about position hold, but it's GPS based. You can also bring in the flight director altitude hold, and it'll hold the aircraft in position to set altitude for until the fuel runs out. Our vision for this also is when you get into a situation where you might have a degraded visual environment, whether that's due to snow or sand, or it's just kind of nasty outside because you've had to shoot an instrument approach somewhere, this is going to help reduce that workload and allow the pilot to bring the aircraft in for a safe landing. Okay. We already talked about queuing. And if you take a look, some of these things come from this pie chart on the right. We're trying to reduce that contribution to aircraft accidents that are induced by the pilot. You can see it's about 42%. That's a pretty, it's not an overwhelming majority, but it's a significant contributor to the number of accidents that are experienced in the rotorcraft world. So we're trying to do things with the aircraft to advance that technology to reduce that big red section of the pie. So that's, if you take a look back through the slides and things like that, you can say, okay, well, that's why they did that, or that's why they did that. Okay, some of the other things here, I'm not going to go through all the other things, but as with all aircraft anymore, ADS-B in and out. Okay, so we've got that. So we've along with the ADS-B in and out, we've got weather and traffic, which is a real big help around here, especially in the Dallas-Fort Worth area. We've got the country's busiest airport, in addition to all the general aviation traffic that takes place out of this area. We've got terrain awareness that comes in handy, and that's everything from the Earth itself, and then all the stuff that we put on as human beings, whether that's towers or windmills or anything that sticks up out of the ground that we might hit. Let's see, we already talked about other things as far as the rotor is concerned. We've got cameras on the aircraft, so we can take a look at the tail rotor from one of the MFDs. We can take a look in the baggage bay to make sure everything is right within the baggage bay, whether that's fire or load shifting, all that kind of stuff, things that an operator is going to care about. All right. So fly-by-wire, some of the other safety benefits, we talked about these, but we got, from a hardware standpoint, 10 to the -9th reliability. We talked about the actuators. Some people might ask a question here about, well, what happens? So we've got two types of augmentation. It's always fly-by-wire, but we've got an AUG-on mode and an AUG-off mode. We normally fly in the AUG-on mode, which gives us all the higher level functions that I already talked about, turn coordination, heading hold, et cetera, et cetera, et cetera. We can also back off one mode and take away those upper level functions that go AUG-off. We're still fly-by-wire, but the AUG-off, it's amazing to fly this aircraft. People get kind of freaked out when they hear about degraded mode. It's transparent going from AUG-on to AUG-off. You have to work your feet a little bit more just to make sure that you maintain the trim ball in the center, but that's about it. Then we've got design assurance level A for all of the electric systems. Don't want to get into that. Okay, so I talked about some of our customer evaluations. This is some of the stuff that we've heard back from the customers. They say it's a dream to fly. That's kind of what we expected based on our experience, but it's nice to hear that from other people, that we're not just biased in our opinion in aircraft. They think that hey, this is a huge step forward in terms of where the rotorcraft helicopter industry is today compared compared to where the 525 is taking it. They've also said, hey, listen, from a Part 29 certification standpoint, the 525 is how all aircraft should fly. It's incredibly smooth. You don't know how fast you're going, unless you actually take a look at the instruments. It's kind of like driving, in my opinion, if I had to compare it to someone, but you drive a really high-end car and it's well insulated and things, and it's smooth, and you look down and you're doing 90, and you thought you were doing 50. It's the same kind of thing here. The pilot queuing in terms of the flight controls, extremely helpful. Helps keeps the pilot's eyes outside, which is what we want. We want the pilots looking outside, paying attention to the world, and not having to just maintain that basic aviating part of it that we talked about. Plenty of power. Once again, that's your guys' engine. At least the GE people on board. Auto rotation assistance is a game changer. And anybody that flies helicopters knows that for airplanes, airspeed is life. Well, for us, rotor RPM is life, especially in the event of an engine failure. The fact that the aircraft will take care of that initial reaction for you, trim you back to that best rate of descent airspeed and keep the NR where it needs to be, it's huge. We also have a go-around button that's part of the flight director, so you hit that and the aircraft will just fly away at 80 knots up to whatever altitude you set. So if you are coming down an approach and you don't break out and acquire the aircraft environment or the runway environment for landing, you just hit that button. That VFR to IFR back to, IFR to VFR back to IFR transition has caused a lot of accidents. We've taken care of that, with the flight director go-around button. And then great visibility. People like to see outside. They don't want to be cooped up in a tin can and not being able to see anything. It helps for passenger comfort, crew safety, all that kind of stuff. Okay, that ends my presentation. I'm sorry I went a little long, but I'm happy to take any questions that you guys might have at this point.
Yeah, Joe, I thank you, Joe. That was actually fascinating, and I think we could have listened to that all day. There was just so much information there, and I'm sure there's a lot of questions. I do believe the webinar time's out, and so I think we've got a hard stop at 1 o'clock. So it's probably not any time for questions, but I just wanted to once again thank you for that presentation, and we look forward to seeing the aircraft certified and enter into service. So thanks again, Joe, for speaking to the East New England chapter of the Vertical Flight Society. And so on behalf of the society and myself, Harry Nahadas, I appreciate you doing that, and wish you all the best. Thank you.
Well, once again, and on behalf of myself and Bell as an organization, really appreciate you guys hosting us and being able to talk about the aircraft. Once again, sorry for going on. I could talk about the aircraft all day long. But if you guys get a chance to come down and see it, whether it's here in the Dallas-Fort Worth area or out at HAI, when we start back up with that stuff again, please come on out, take a look at it. Really appreciate it. I love it personally when, especially when we talk about suppliers and things like that, people who don't actually get to see, where their products end up. We'd love it for you guys to come out and see, oh, hey, that's what you're doing with our engines, or, with our generators, or whatever. It's a pleasure to see how all these things come together. I mean, I know we're different companies, different organizations and stuff like that, but really it's a team effort. It doesn't take place, in a vacuum. And there's literally hundreds of people, behind me. I just happen to be the face today. But it's not my work that got us to where we are. It's the 99.9% of the other folks that work diligently, day in and day out to move us forward. So once again on their behalf as well, appreciate the opportunity, and hope to get together with you guys again soon.
Okay, very good. Thank you. Bye-bye, everybody.
Bye now.